Hi, this is George Buzzell here, giving my third module for SAT 611. And unfortunately, I couldn't get the video capture to work. I can only do the screen capture, so I hope you just bear with me here and you can hear me just fine. Okay, so I'm going to be talking about the general linear model, or the GLM, which is essentially an underlying model that describes both ANOVA and regression. It's a linear model, hence general linear model, that's used to predict some dependent variable. You can describe the GLM, the overarching GLM, using an equation that is y equals b naught plus bx plus e. And I'll talk about what each of those various aspects of the equation mean. So first, y is obviously what we're trying to predict. It's the dependent variable. And we're trying to predict it, but obviously we do an imperfect job of doing that. B naught is the intercept of the equation, but more importantly, you can think of it as our best guess if we didn't have any predictors. So if we didn't have the rest of the equation, that would be our best way to guess what y is, what our predicted is. X of the equation represents, it can represent just a single variable, or it can represent several variables, in which case x becomes a matrix instead of just a vector. And it's the predictors we're using to try and predict a value of y above and beyond just the intercept. And the weight of each predictor that we use in the model, how much each predictor influences our prediction of y, is described by b. And it's essentially what I just said. It's the weight each predictor has in the model of predicting y. It's also known as the coefficient of x. And then finally, E refers to residual or error, depending if you're talking about multiple regression or ANOVA. Basically, it just reflects that we don't perfectly predict y, that there is some regression, or there is some residuals left over that are unpredicted or error. And that's what that reflects. Okay, so as I said, the GLM covers both ANOVA and regression. And there's obviously many similarities between ANOVA and regression. First off, they both hold the same assumptions. You have to meet the same assumptions in order to properly use the techniques. And so for both ANOVA and regression, you assume that the relationship between x and y is linear. Again, related back to the idea of general linear model. There also should be no errors of commission or omission. And by omission, we mean that all necessary predictors are used. However, that might not always be the case, but that's the assumption we're shooting for. That's the ideal. There's no measurement error, which of course is never met in practice. That's just not ideal. I mean, that's just not practical, but it is the ideal we're shooting for. That's the assumption of both ANOVA and regression. The mean error of the residuals should equal 0. And there should be homoscedasticity. There should be no heteroscedasticity, which basically occurs when the variance of the residuals is correlated in some way across one of the predictors. The errors should be random and uncorrelated. Errors should be normally distributed. And the predictors should be independent of each other. So there should be no multicollinearity. If there is multicollinearity, there's some sort of relationship between the predictors, then we run into problems with our hypothesis testing and finding a significant model. So those are the assumptions that must be held true for both, or those are the ideal assumptions for both ANOVA and regression. But there are, of course, differences between ANOVA and regression. Most notably, ANOVA is a measure of difference. You're trying to see if there's any difference between two group means. And so it's based off of the f-test, which is essentially just t squared, the classic measure of difference. And so because you're trying to look at difference between group means, any deviation from those group means is viewed as error and treated accordingly in ANOVA. On the contrary, regression is in a measure of association. It's essentially a measure of association, and it's based off of the correlation coefficient. That's the basis of it, just like the F-test is the basis of ANOVA. The correlation coefficient, to learn more about it, you can always read Rogers and Nicewander, who go back and basically do a history of the interpretation of it, of the correlation coefficient, going all the way back to Galton and Pearson up to relatively recent interpretations of it. But the important thing is that basically the correlation coefficient is the basis of regression. And getting back to regression attempts to look at the association between the predictors and the predicted, the y variable, and we model that relationship using a line of best fit, a regression line. And further, any deviations from this line, the individual observations as they deviate from that line, is seen as is called residual, not error, and that reflects the idea that we failed in our model. We failed to perfectly predict the relationship, and not that those are in fact errors. And so, in multiple regression, variance is attributed to individuals, while in ANOVA, it's attributed to groups.